Hello and welcome to the sixth segment of the Geographical Peculiarities of Kuttanad, its environmental issues and solutions through engineering. So, in the previous 5 segments, we have been discussing with regard to the geographical features of the particular place, the past and present flood, its effects on Kuttanad, some of the flood mitigation and adaptation measures in the place, then some of the works which have been conducted in the place with regard to housing sector, with regard to the polder water construction, with regard to canal rejuvenation, etc., etc. Now, in this particular segment number 6, we are going to discuss about some of the structural failures which have happened in the place, not only because of flood, but because of other reasons also. The soil is a culprit in the failures of certain structures, so we are going to see that. And after studying about those things, say some of the protocols which are evolved for resilience in construction, that also are going to be discussed in this particular segment. So, we go from here. As we see in the pictures, this is a typical example of a structural failure which happened in the place. This is a school building. If I go to the story of the building of the school, a little bit behind the failure of the school building, say there was a building which was existing in the locality, which was of 100 years of age, and that building was constructed. It was like a thatched building. It is having a tiled roof also, usual wood as well as say the building blocks which were available at that time, they were made use of for construction. And because of the age of the building was supposed to be demolished, because it is of more than 100 years of age, it was supposed to be demolished and a new building was supposed to be constructed over there. So, plan was made. Actually, the plan was brought from some other place. It was not actually made for that particular place, and accordingly a contractor is entrusted to do the work. So, the engineers of the Panchayat and PWD, they were involved in that matter. The building was constructed with a plan which is brought from elsewhere, as I told you already. It was a 2-storied 12-roomed building designed as a framed structure, and before the construction of that particular building, the contractor removed the sand available from that place. When he dug down for the foundation of this building, he saw that there is a thick sand deposit of 10 feet or 3 meters high, 3 meters depth. So, he removed the sand from there, pure river sand from there, and refilled the place with other kind of materials, maybe the sand available, maybe the soil available from elsewhere, and the kind of things. And then the construction was partly made on that newly filled earth and partly on other part of the site. So, what happened was, after 2.5 years of its construction, the head teacher of that school, she heard one day the tiles are falling down, the sound of the tiles falling down, the wall tiles falling down. And then suddenly she asked the students as well as faculty members to come out of the building. Everyone came out of the building, and within 1 hour of them coming out, one part of the building came to earth, as you can see in the first and second picture. One part of the building, the part where the class was going on, the part where the faculty room was there, the part where the computer lab was there, that came to earth. Later it was inspected. During inspection, it was noticed that not only the structural design was there, but foundation design was also not there, and adequate foundation was not given to the structure. So, with having no consideration at all to the soil in the place, the foundation was designed and constructed. As you can see in the picture, some of the beams as well as columns which you can see over there are very thin. The columns specifically which you see in the third as well as fourth figure or fourth picture, they are made of bricks, clay bricks. RCC is not there, no kind of reinforcement is there, no concreting is there, but only clay bricks. and the columns failed under shear failure. The beams are of very thin cross section. The reinforcement, steel reinforcement given in beam was not adequate. So we can say plenty of reasons like that. And in addition to this, before constructing the foundation, they have removed a tree also from the place. So that gap was there. Refilling to the place where the tree was initially standing was also an additional problem. So in short, the entire building came to earth because of several reasons. One, the soil was not considered for design. Second thing, a design which was available elsewhere is brought to the place and it was executed over there. Third thing, there was no kind of structural design. The columns were made of bricks. The beams were not adequately reinforced, and slabs also were not adequately designed. So we can say plenty of reasons just like that. This is a typical example of structural failure which happened in the place. You can see when the place was dug down for the soil investigation, you can see that top, say 60 centimeter to 1 meter layer was red earth filling. Below that you can see a dark color. The dark color is dark clay only, and you can see water table also, which is very high in that place. And in the third photograph, we can see the inverted T-beam foundation, which was of course inadequate for withstanding the load coming from the superstructure. So this kind of construction has been practiced without much engineering in the place. If you look at the residential buildings which are constructed over there in the recent past, you can see that the foundation is not going deep into the soil. Rather, the foundation of those buildings are standing on the soil, on the top soil, considering that the top soil is good than the soil below. But without having much anchorage, there is every possibility of washing away or toppling down of the structure. So some of the possible causes of failure of structures based on this example and other examples which are available in the locality, they may be summarized in the following lines. Wrong choice of land for construction. Many buildings are constructed, many structures are constructed in floodplains. Many structures are constructed in places which should not be chosen as say soil for construction. Without having adequate soil stabilization, people go for construction. So wrong choice of land for construction, that is one. Then settlement of soil below the foundation and differential settlement of structures. That is a very common phenomenon. Settlement will be there for the structures for sure, but differential settlement, if the settlement is different from one point to the other point of a structure, the structure is going to fail for sure. The structure will tilt and there can be cracks in the structure in the building, and finally it causes failure of the structure. So this is a major cause of failure. Construction on soft soil with low bearing capacity. As we saw in some of the previous segments, the soft clay available there did not offer much bearing capacity to structures, to loads. So such kind of, if you construct buildings on such kind of clay without any soil stabilization, there is every possibility of failure. Then construction on top soil without much anchorage of the foundation, that is what I was mentioning in the beginning. On the top soil, they construct the buildings after ramming, thinking that sufficiently ramming the earth is good enough to give a good bearing capacity. But the compaction of soil, that may be good in the beginning, but consolidation is not taken care of. The pore pressure is supposed to go off and the soil will consolidate. The grains will to each other, stand close to each other after pushing away the pore water and the pore gap in between. So that process will take over a time only. It will not happen immediately. So if you construct a building immediately after filling a particular site and construct the foundation immediately above that, then there is every chance of consolidation settlement and the building failure. Foundation on recently filled up soil. This is also added to the previous statement. Then washing away structures owing to storm water flow, lateral instability. So when the structures are constructed just above the soil without having any kind of anchorage, when there is storm water flow, there will be seepage of soil below the foundation, and every possibility of failure of structures can happen. So the structure may tilt and it may fail. Then sometimes some of the buildings are having water absorbing building materials. This also was noticed in the place. During several inspections, this point was also noticed. Many of those building materials which are used may be having water absorbing property, and owing to water absorption they may become soft. That is also a cause of structural failure. Then extensively, nowadays people are using extensively this RCC, reinforced cement concrete, but without any kind of design based on IS codes or detailing. So if RCC is used, they use RCC for their foundation, they use RCC for their superstructure, they use RCC for the roof also. Somebody may think that I have inspected one building say in one point of time, and I was wondered about the amount of load which they have put in the RCC structure over there. They thought that if you add RCC to the structure, that may strengthen the entire structure. So there was a 90 centimeter thick foundation given with RCC. Do you believe this? 90 centimeters thick RCC, and so much of reinforcement. Reinforcement was very, very heavy, without any design for sure, but heavily reinforced structure. And above that, they constructed the building, the superstructure, and the roof also was RCC roof. They confined the boundary also with a strong compound wall, and inside the compound they have laid this tiles, granite tiles or other kinds of tiles. So fully tiled compound. After say 6 months or so, they observed that these tiles are bulging up. The building is there, the two-story building is there, the center, and the tiles besides in the compound are bulging up, just they are getting bulged up, because there was tight compound wall in the boundary, and there is a central shear happening because of the building. The soil between the compound wall and the building is getting bulged up. So there is a common bulbing phenomena was happening over there. The building is settling down, and the building has cracks also. The building is settling down not in the same pattern. At one point we measured the settlement also, but one point the settlement is 2.5 centimeters. At another location, which is say diametrically opposite to that corner, the settlement may be like 10 centimeters. So differential settlement was there. The building initiated cracks, and finally they wanted the building to get raised up. That is also a common thing which is happening there, the building getting raised up through jacks and things like that. So what is happening in such kind of say non-engineered construction, like design of RCC without any using of RCC without any design or detailing, is that the enormous amount of load is put in the form of RCC or other materials, and that will preload the newly filled up soil, and the soil cannot bear that much load. So without having any concern with regard to the bearing capacity of soil, without having any concern to how much load the superstructure is going to put in that particular site, people are doing such kind of construction. So that is also a cause of failure. Then of course poor construction practice of superstructure. We may look into the facilities which we require in the superstructure, the function of the building, but not the structural strength of the building. And finally, the structure is supposed to transfer the load to the foundation and to the subsoil. So this fact is also not considered while designing the superstructure. Inadequate supervision, even if the structure is designed by an engineer, unless there is a supervision by the same engineer or somebody else throughout the entire construction period, there can be faulty construction practice, and finally that may also lead to structural failure. Now we can see in this slide a typical soil investigation report in a borehole in Kuttanad. You can see in the top 1.1 meter or so there is a filled up soil, and below that you can see loose clay having a thickness of 14.9 meters or so. Below that you can see clay sand of thickness of like 7.5 meters or so. Then stiff clay is below that, and you can see hard soil just below that. So, this is a typical kind of a soil investigation report in a borehole in Kuttanad. The N value, the standard penetration test values are also reported in the particular chart, but you can see in the first and second layers they did not report even a standard penetration test value, because the hammer is just going down just like that without having even a single blow. So, the number of blows required for 15 centimeter, 30 centimeter and 45 centimeter penetration is treated as that is a parameter for this N value or the standard penetration test value. But even with only a single blow, the hammer is going down this much say penetration in the top, like 15 meter or more than that depth. But below that you can see the hammer penetrates through those much centimeter or that much settlement by 2 blows in the next layer, that is 7.5 meter layer. Then further when you go down, you can see the penetration number of blows required is more than 40, and finally you can see when you go deeper than 40 meters in the particular site, you can see the number of blows required is more than 50. And when the number of blows is more than 50, we consider that particular layer as a hard strata, and the foundation can be placed on that layer. That is part of civil engineering. Now, another typical example is given here, where on the top soil you can see a few number of blows for that much penetration. There is also, you can see filled up soil, and black clay soil is there in as a second layer. Then loose clay is there as a third layer, which is much thicker, and stiff clay is there, and finally you can have much more harder kind of a strata. Here also hard strata is available at more than 40 meters depth. That is the point which I was trying to bring about over here. Now, if you look at the soil investigation report of some other sites, you can see that after going down by a distance of 10 meters or 15 meters, you can see there is a 3 meter or more than that a thick layer of shell deposit, and that shell deposit is much good in bearing pressure or bearing load from the foundation. So, in such kind of sites, many a times buildings of 3 stories or more than that are founded on that shell layer. At the shell layer, usually the N value or the standard penetration test value is more than 30, more than 40 of that order, and that is sufficiently good for having a bearing capacity of like 150 to 240 kilonewton per meter square. All right, now we can see a typical case studies that is going to be explained in the next segment only, but here you can see when we visited a site in Kainagari, which is one of the low-lying places in Kuttanad, a house which was fully demolished during the 2018 flood. Nearby the house there was a toilet block, and this woman is showing the level of water rising during the 2018 mega flood. And at the same site, when we tried to dig down, the water table was available say up to a depth of 30 centimeters or so. This is done during January. So, water is available if you dig down by a small depth. So, based on the observations which we made in different sites, and based on the parameters we identified with regard to the causes of structural failure, certain protocols are being proposed for resilient construction to live with water. You cannot avoid water for sure for over there, but you can have some resilient construction practices over there for sure. So, those construction practices are supposed to be simple, they are supposed to be borrowed from indigenous technologies and some adaptable technologies also. So, the prime thing is recently reclaimed land, river basins, wetlands or places prone to landslides should be avoided for construction. Well, the term landslides may not be applicable to Kuttanad, but it is applicable elsewhere. It is a general statement. It is can be adapted in any place in the world for sure. So, recently reclaimed land cannot be used. River basins, wherever the water is supposed to flow, is not supposed to be used. Wetlands, should be avoided for construction, or places which are prone to landslides, they are supposed to be avoided for construction. Then the bearing capacity of soil may be improved by proper soil stabilization techniques through adaptable and indigenous techniques. That is the prime thing which we have attacked upon during our through our projects. So the soil stabilization techniques were done through certain adaptable as well as through indigenous technologies. For example, bamboo piling is one among them. Bamboo is a plant which will grow in water, which will stand in water without any kind of decay. Coconut trunks, they also stand in water without any kind of decay for long years. Then coconut shell can also be used as a soil stabilization technique. Well, this is actually borrowed from the bund construction techniques which we have seen in one of the previous segments. So I will explain about say such kind of techniques in along with certain case studies in due course of time. Now, loads on structures can be distributed to a large area where soil depicts low bearing capacity. Well, that is a very important thing. Wherever there is possibility of low bearing capacity of soil, you can increase the breadth of foundation, but that is to be designed. How much width is to be breadth or width is to be increased for the foundation is to be designed based on the soil bearing capacity at that particular site. That depends upon site to site. The level of basement may be decided based on the history of average flood level. You would have noticed that in one of the previous segments we have discussed about the adaptation of the people who were living in Kuttanad earlier. They constructed their elevated plinth, they constructed their mezzanine floor to be adaptable with flood. So whenever there is a flood, they stayed in the mezzanine floor. Whenever the flood comes above their plinth level, they stayed in their mezzanine floor till the time when the flood resides down. So they can have a kitchen also in the mezzanine floor above, and they can stay there happily, they can live with water. So the level of basement which is constructed for new buildings can be decided based on the history of the average flood level, not the maximum flood level, for sure. Total load of the building can be reduced through use of lightweight building materials. Nowadays AAC blocks kind of things are available, so you can use such kind of building blocks, but not for load bearing, of course. Load bearing structure can be a different one, and filling structure can be this kind of aerated blocks, things like that. But the total weight can be reduced in because of the use of such kind of materials. There are certain school buildings which are constructed in Pulingunna, in Kuttanad, so that the total weight of the structure is reduced by 70%. 70%, you don't believe that. You can see such kind of improvisation after the 2018 floods in quite common in the place. This was a photograph taken by myself during a travel, a boat travel. So this is a typical house which is standing on stilts. You can see the water body on this side, on the front side, and you can see the paddy field or the polder on the other side. The thin bund which is separating the two is made use of as a residing place by persons, by the people over there. And you can see it is a tin house. Two families are staying in the tin house. Elevated plinth for sure, through stilts, through columns. But unless the stilts or the columns are designed properly by an engineer, there is every possibility of shear failure. That is, one column offers very much load to the soil below, and if the soil below is very weak, there is every possibility of settlement of that particular soil. The column may go down, and accordingly there will be differential settlement for the entire building. The building may come down. So the columns have to be designed properly. The foundation below that, it should not be individual footings, but the footings have to be continuous. You cannot have individual footing for each column. You have to have a connection between the footings also, the foundation. So unless there is a proper design for the foundation, this kind of structures are also vulnerable. Well, we continue with the resilient practices. Use of codes of practice is very important. So Indian standard codes are there for design of structures. That is to be followed for sure, but nobody nowadays, when we construct a small building, nobody follows such kind of codes. That is detrimental to the structures. construction shall be well engineered and supervised. So, if the codes are practiced, code of practice are used, if there is proper design for foundation as well as superstructure, and if it is supervised, then you can say that the construction is well engineered. So, there has to be a team of engineers for such kind of structures, and specifically for Kuttanad you require a special team of engineers for sure. Then horizontal and vertical RCC bands can be practiced to make parts of buildings act together. This is a piece of information which is collected from research of IIT Chennai. So, like 10 years before or so, during that time they experimented something in the IIT Chennai to safeguard against earthquake. The buildings which were constructed with horizontal as well as vertical bands, they withstood earthquakes to a better compared to other buildings. So, what happens when you have RCC bands or say steel bands which are horizontal as well as vertical in the building is the entire building is considered as just like a single unit. So, whenever there is settlement of one part of the building, the other part of the building safeguards it. So, the kind of differential settlement is going to be safeguarded through this horizontal as well as vertical bands. That is the advantage of this kind of a construction. For example, you can see the lintel bands. The lintel is a continuous thing in a building, and wherever there is corners in a say between, wherever there is a junction between two walls or wherever there are corners, you can have a column over there. Though that can act as a vertical band, the lintel band, the band in the roof level and the band at the plinth level, they can act as three layers of horizontal bands, RCC bands. So, they will tie the building together as a single unit. So, differential settlement can be taken care of very effectively by this kind of bands. That is also proved by certain experiments. Then use of quality building materials. The building materials which are to be used in such site, they have to be tested from the samples of lot of materials. Samples have to be collected and they have to be tested in a good testing laboratory before they have to be used as a building construction material. Then construction can be cost effective. If you make use of locally available building materials, you can make your construction cost effective also. So, these are some of the kind of resilient protocols which were made to do the building construction, with living with water in the place. Now, two photographs are included here as the last slide in this particular segment for retrofitting. So, I was telling you about the horizontal as well as vertical bands. Now, here you can see this is a typical example of retrofitting of a building where there were vertical as well as inclined cracks generated in the building due to the 2018 mega flood. It happened in Kottayam, not in Kuttanad. It is part of Kottayam only. So, there were because of settlement of the structure, there were cracks in the building. Cracks would be vertical, cracks would be horizontal, cracks can be inclined also. So, the building was a masonry structure, and you can tie the building with the steel bands, with vertical as well as horizontal steel bands. So, these steel bands are going to tie the entire building as a single unit, and when you tie it up with screws and things like that, the cracks are going to close together, and later development of cracks, widening of cracks can be avoided in such buildings. So, kind of retrofitting also can be done. So, these are some of the resilient protocols for building construction in the place. Thank you.